Okay, today this is Niall Hird. He's from the University of Glasgow, and his title, this is some abbreviation, invariant subalgebras, but there is something more in the official. Okay,
Yeah, it's quite a long title, so
okay, you have the word.
great, thanks. Yeah, so I'm going to be talking about these invariant subalgebras of the rational Cherednik algebra. There's two of them in particular that we study, and the full title's quite long, so hopefully it becomes clear as the talk goes on. Right, so this is joint work that I did with Gwyn Bellamy and Misha Fagan over at the University of Glasgow. Just want to say that at the start. Right, so an overview of the talk. So I'll begin with just some basic definitions. So first of all, the rational Cherednik algebra, because I presume some of you haven't seen that before. Also the associated graded of an algebra, which I guess more people are probably familiar with. Then we'll discuss the Poincare-Birkhoff-Witt theorem, which is one of the first theorems that you encounter when you study rational Cherednik algebras, and we'll see why it's relevant for us as well. And then we'll discuss the center of the rational Cherednik algebra just more generally and what we know about it so far. Then introduce the two subalgebras that we're actually interested in our research, talk about an interesting connection with Lie algebras, and then finish with some actual results on the centers of these invariant subalgebras, which is the goal. Okay, so to define rational Cherednik algebras, you need to know what a complex reflection group is, so that's not too bad. So if you've got a complex vector space H, then a complex reflection is just some linear map that fixes a hyperplane. So you've got the dimension of your image of that map minus the identity is just equal to 1. And a complex reflection group is just some finite group that's generated by complex reflections. So now we've got the definition of rational Cherednik algebra, which at first can seem maybe a little much, but really it's not too bad. You just build it up in steps. So given your complex reflection group W, we have our vector space V here, which is H plus its dual, H being the space that W is acting on. Then you've got a natural pairing from H and its dual into C, right? Just do the most obvious thing you can think of. If you've got Y and H and X inside the dual, you just calculate X of Y. So this allows us to define a symplectic form. And if you don't know what that is, don't worry about it too much. It won't really be relevant for the maths that we discuss going forward. Which on the right-hand side, these brackets is just this pairing that we define above. So you could rewrite that as x2 of y1 minus x1 of y2. And I'm going to denote by this capital S all the complex reflections in W. So these are things that generate it. Then for each S, we make a new symplectic form that's equal to omega or W on the image of 1 minus S and 0 on the kernel of that. And so you just denote that by an omega sub S. And so we're almost there. So we've also got some scalar term T inside the complex numbers. And C is some conjugacy class invariant function that goes from the complex reflections into the complex numbers. Then the rational Cherednik algebra for T and C is defined to be this quotient of the tensor algebra of V, semi-direct product with the group W, quotiented by this ideal here. So this ideal, what it tells you is how to commute things in H and things in H dual, right? The semi-direct product gives you the rules for how to commute things in V with things in the group. If you want to move something in the group from your left to your right, you have to act on those things in V, which you know how to do because W was a complex reflection group, so it comes with this action. But you don't know how to commute things in H and H dual each other. So when you do that, you get this kappa term, and that's defined below, but don't worry about it too much. Memorizing this sum for the rest of the talk, you won't need to. It won't appear explicitly for us for the rest of the talk, so you can forget about it. There's only two really key things you need to remember about this kappa. So the first is that it's entirely contained inside the group algebra, right? This first term is T times omega times by the group identity. And then you're just got a sum of scalars times by these complex reflections. So that's also inside the group. Second key thing is this kappa is entirely determined by the T and the C. So that's why we say that T and C parameterize the rational Cherednik algebra. So the associated graded of an algebra, if you've got some algebra A that's filtered, so by that I just mean that you've got an increasing filtration by subspaces, just vector spaces inside it, Fi, and the A is equal to the union of these, you can make something called the associated graded of A. And the associated graded of A is just a direct sum of the quotients of these Fi. So just Fi, quotient Fi minus 1 is your ith part of the associated graded. So your addition is the same as in the algebra before, and everything sort of looks the same except for multiplication. So the multiplication is different here. So how do you multiply things? So if you have, say, x in Fi and y in Fj, you just multiply x and y together, and you get something living in Fi plus j, right? And so what that does is all the lower order terms that come from this multiplication, the ones that live, if you can see my mouse, in Fi plus j minus 1 here, they just get pulled into that and forgotten about. So the multiplication is simpler in a sense. You just forget all the lower order terms when you multiply things together. But while I say it's simpler, and it is, and it allows us to work with something maybe a bit easier, it can also be subtle, and you get things that you don't expect. So you have to be careful. So there are some important properties of associated gradeds. So these were 3 key properties that we found that we were using again and again and again in our paper. And they're quite easy to derive as well. So we just have this lemma right at the beginning of our paper, which says that if you've got some filtered algebra A, then it's true that if B, this is the first part, if B is a subalgebra of A, then you can make a filtration of B just by intersecting each of these Fi's with B. So you can make the associated graded of B, and that's a subalgebra of the associated graded of A. And our claim is that if the associated gradeds are equal, that means that B is equal to A as well. Our second claim is the associated graded of the center of an algebra is always contained in the center of that associated graded. And the third is really the reason that we consider reductive groups for this talk. So if you have a reductive group acting on your algebra, and each Fi is stable under this group G, then this group also acts on the associated graded of A, and the associated graded of the invariants of A under this action, pardon me, is the same as the invariance of the associated graded under this action. So in notation, it's a lot easier to read than words, perhaps. So you can just pull this G outside the bracket, which turns out to be very useful. Okay, so we have the rational Cherednik algebra. We have our associated gradeds. How do we start mixing them together? So the rational Cherednik algebra has a sort of canonical filtration, and it's given by setting the group to be in degree 0, your vector space V that you form the tensor algebra with to have degree 1, and then your Fi's are just the ith degree part. So because the associated graded, because we're in the associated graded now, it turns out the commutator of xy minus yx is equal to 0. So to see this, xy minus yx is equal to kappa. That's just from the defining relations of the rational Cherednik algebra. And on the left-hand side here, xy minus yx, both of these terms have degree 2, so this whole thing has degree 2. But on the right-hand side, kappa is entirely contained inside the group algebra, right? And the group algebra has degree 0. So the only way that these can be equal is if they are equal to 0. So this observation gives us a map from the symmetric algebra of our vector space V, semi-direct product with our group, into the associated graded of H for any kappa. Kappa is sometimes an alternate notation to the T and the C. So we've got a map here, and also I included, because it makes it a bit clearer, if you have T and C both equal to 0, this is equal to S of V, semi-direct with double, right? Because if T and C are both 0, Now go back a couple of slides. This kappa term just becomes 0. So it's the same thing as saying that x and y commute. Right. And we say that the Poincare-Birkhoff-Witt property holds if this map given here is an isomorphism. So the PBW theorem, like I said, is the first sort of significant result you see when you're studying rational Cherednik algebras. And what it says is that this is an isomorphism if and only if we've got C and T, and kappa has this form. So precisely the definition of what a rational Cherednik algebra is. So that has some important consequences. So associated gradients as algebras are often very different to the original algebra because the multiplication is often so strange, really, when you start working with it. They are always isomorphic as vector spaces. So since we've got a basis of H00, or the symmetric algebra of V semi-direct W, so if we know a basis of that, then we can get a basis of every other rational Cherednik algebra, which turns out to be an enormously useful thing to do. Okay, so what do we know about the center of the rational Cherednik algebra already? So first of all, it's pretty important. A lot of the representation theory, the structure of the rational Cherednik algebra, and certainly the geometry of it all depend on the center. So it's something that we want to study. We also know that the parameters T and C obviously affect it, and T much more so than C. So if T is equal to 1, then the center is trivial. So it just means that it's the field that the algebra is over. So it's as small as it can be. But if T is equal to 0, then you have a really large center. So what I mean by this is that your rational Cherednik algebra is usually this infinite dimensional guy, but it becomes a finite dimensional module when you consider it over its center. So typically pretty large. And then it's due to Ettinghoff and Ginzburg that we know what the center is of the rational Cherednik algebra for T and C both equal to 0. So we know that quite explicitly. Like we know it's this, this is just applications of the PBW theorem, the first 3 equalities, and the last one is really the new one here. So we know that the center is actually just the W invariants of the functions on our vector space V, which is good. It is pretty good. But even then, if you want to write down an element of the center, like explicitly what an element is, it's still very difficult to do. Just knowing that, yeah, doesn't make things too much easier. But it is good. So another kind of tactic then, the center is really hard to understand, but maybe we can pick some subalgebras of H and we can better understand those. Maybe the problem gets a bit easier. So that's what we did. So the first one we considered, we got by coming up with a new grading. So we set the degree of H to be -1, the degree of W to be 0, and the degree of H dual to be 1. H, remember, is just the space that the group is acting on. Then you can consider the subalgebra generated by all degree 0 elements. So in the PBW filtration, this is just the even degree elements. But it's simpler in this notation. So yeah, so we asked some questions initially when we started, like, can we just describe what the center of this is? How does it depend on T and C? And yeah, it is still a pretty difficult thing to do. I should mention as well that it's not a trivial question yet to ask what does the center of H T equal to 1 look like for this degree 0 thing. Just because the center is trivial of the entire rational Cherednik algebra, it doesn't mean the center of this subalgebra would be trivial. So still be non-zero. Yeah, we realized these are pretty difficult questions. So we tried to get a better understanding by comparing it with other subalgebras and seeing what we could determine about that. So we took Z of H0 on the inside, that's the center of this degree 0 part, and we compared it with the degree 0 part of the center. So that's this part on the right here. So we take the center of the whole thing and then take the degree 0 part of that. And so if you play around with it for a little bit, you'll quickly realize you've always got one inclusion, which is that the degree zero part of the center is always contained inside the center of the degree zero part, right? If you take something inside the degree zero part of the center, then it has to be in the center. So it commutes with absolutely everything in our Cherednik algebra. And it has to have degree zero. So that means that it commutes with everything that has degree zero, and it has degree zero. So it's in the left-hand side. But it wasn't obvious to us if this was an equality. Sometimes, always, never. Yeah. So first thing to do is try an example. So the very first example you try and do is you take the symmetric group of order 2, right? The non-trivial example. So this has got some generators, x, y, 1, and sigma, and we've got these relations as well. So here, sigma, since it's our group thing, if we try and commute it with x or y, we have to act on it, like we did with the complex reflection. It comes with this action. And so here it just takes x to minus x, it takes y to minus y, and the commutator comes from our rational Cherednik algebras that we saw in the definition. Okay, so it turns out the center of this thing is generated by the elements 1, x squared, y squared, and this last term, xy minus c sigma over 2. So we just got some calculations to check that that's correct. So if you're interested, you can read them. I won't read it all out because it's a fair amount of equal signs. But we just check that x squared commutes with y, and it commutes with the groups term as well, sigma. And the calculations for y will be identical. And then for this last term as well, we also have to compute that. And it takes a little bit more work because the Cherednik relations, the commutator relations come out a bit more, but it's not too bad. Okay, so we find that these are all the things in the center. But this example is quite interesting because it actually answers one of the questions from the last slide, right? So it tells us that this inclusion is proper, at least in this case. So if we take the element sigma, this belongs in the center of the degree zero parts, right? It has degree zero, and if you're another degree zero element, you look like xy or something in the group or some product of those. And sigma commutes with xy, just via this sum, right? You bring it across twice, so you'll get minus 1 squared, which is just 1. And yeah, it certainly commutes with the rest of the group, right? It's just S2. Yeah, so it's inside the center of the degree zero part, but it's not inside the degree zero part of the center, just because, well, for instance, sigma doesn't commute with x. It takes it to minus x. Yeah, so then we realized this inclusion was proper, at least some of the time. So yeah, there was something there. So what was the difference between them? The second subalgebra that we wanted to study is the Dunkl angular momentum subalgebra. So this is defined only for a real reflection group, right? That's a very key point. Yeah, I'll carry on with definition before I say the next thing. So if you take y1 to yn inside H, and x1 to xn to be its dual basis, so I just mean x1 of y1 is equal to 1, and 0 otherwise, then you can define mij, these elements mij to be xiyj minus xjyi. So it looks a bit like the commutator, but it's slightly different. Then the Dunkl angular momentum algebra is the subalgebra of H generated by these elements and the group W. Yeah, so you can, that's what I was gonna say. So you could try and do this for complex as well, complex reflection groups. And the definition still sort of makes sense. It's just you end up getting far too many elements generated by this algebra than you expect, and it becomes very difficult to deal with it. Okay, so now we're finally getting to more of the point of the talk. So I claimed that we're looking at these subalgebras as invariants under reductive subgroups of SL2 in the blurb. So this is how you do it. So we've got SL2 here, just the 2x2 matrices with determinant 1. Then this has a canonical action on rational Cherednik algebras. If we've got a matrix A, B, C, D here, on your x's, it sends that to AX plus BY, and it sends Y to CX plus DY, right? Yeah. No. Yeah, sorry, where was? Yeah, okay. So then we can think of subgroups of SL2 acting on H and ask about their invariance. So it turns out that the degree 0 part of H is the same as the invariance under the action of the units of C. And to see that the units of C are a subgroup of SL2, just identify any complex number lambda with the matrix that has lambda and lambda inverse on the diagonal. And the Dunkl angular momentum algebra, it turns out, is the same thing as the invariance under SL2, the entire group. So it's just a proof of the first statement. I'm not going to give a proof of the second because it's very similar, but just with quite a few more steps. Okay, so one inclusion is pretty straightforward. The degree 0 part is inside the invariance under the action of Cx. So if we have some degree 0 thing, it's going to look like some number of powers of x, another number of powers of y. They'll have to be the same for it to be degree 0, and possibly some group terms. And when you act on that by lambda, you're going to get lambda to the power of whatever it is for the x's, times lambda to the minus the power of the y's, and they're going to cancel, and then it'll just ignore the group terms, so it's going to fix anything in there. The opposite inclusion, though, this is where we have to use that important lemma that concerned the associated gradients at the start of the talk. So what we do is we show that their associated gradients are equal. So we know that H0 now is a subalgebra of HCX, and that means that its associated graded is a subalgebra of the associated graded of HCX as well. Okay, so we give it the PVW filtration again. Then this is stable under the units in C. And we can use the third part of the first lemma, which, if you want a reminder, so for reductive groups that are stable under, each FI is stable under your group, then you can pull this G outside of this associated gradient bracket, which is really the key step for us. So the associated gradient of HCX is the same as the invariance of the whole associated graded. And then you just use the PVW theorem to rewrite your associated graded. This thing is the same thing as H of 0, 0. So you plug that in, you take the invariance, and you get this, the invariance of this polynomial ring semi-direct product of the group. And then all you have to notice is the Gur H is the same as this, right? Because it contains W, because the group W is inside the degree 0 part by definition. And this ring of invariant polynomials is generated by elements xi, yj, which is a fact that we'll just set aside for now. It's generated by those, and each one of them lives inside the degree 0 subalgebra. Okay, so we also saw a pretty interesting connection with Lie algebras. That when we were originally studying this, like I guess your maths changes, not always chronologically. So we were looking at it from this angle for quite a while before we had the invariant subgroup angle, which made a lot more sense. So I'll explain this because it's still, I think, a pretty cool connection. So you can identify H tensor H dual with the endomorphism ring of H. Again, H, just the complex vector space that our group W is acting on. And how do you identify these two things? So if you've got something in H and H dual, your Y and your X here, so Y is in H and X is in H dual, then what does this do to an element of H? So it just sends it to X of H times Y. So if you've got a Lie algebra G inside your endomorphism ring, you can think of its image in your rational Cherednik algebra under this identification. The tensor product lives inside the rational Cherednik algebra, by the way. So you can consider it inside H, and then just think, right, what's the subalgebra that's generated by the image of G and also W? And so it turned out that for the units of C, it turns out the Lie algebra that generates the same subalgebra is GL of n. And we have an equivalent theorem for the Dunkl argumentum algebra, but it's not here because it's sneakily given in the previous slide, right? So HSON is the same as HSL2, and it follows that same rule. So then one line of questioning we had was, is this unique to these two algebras, subgroups, reductive subgroups, or is there other ones that have this property? Can we find Lie algebras G and other reductive subgroups gamma so that we get this equality? And so it turns out, in general, you can't do this. So, and we don't consider finite groups. So there's only one other reductive subgroup of SL2, which is the normalizer of CX. And you can write this as being generated by the units of C and this element F, where F sends X's to Y's, Y's to minus X's, and group elements to group elements, just leaves them the same. So then we prove in our paper the following lemma, that there's actually a proper inclusion here. So we don't have to worry about the proof, but it is a proper inclusion. Yeah, but then if we consider the invariants under n at 0, t equals 0, and c equals 0, right? Then we have this second equality here. It's just this invariant polynomial ring semi-direct with the group W. And since we have the units in C are inside N, we get this reverse inclusion of invariant rings. This 2 here just means the degree 2 component of it, which will become relevant in a second. But that would be true for the whole polynomial ring. If you drop the 2, it's still the same. If you're invariant under N, then you're also going to be invariant under the group of units C. Right. Yeah, but we use the subscript 2 for the degree 2 component because the degree 2 component looks just like the tensor product of H and H dual. Yeah. So then we can use our identification between H and H tensor H dual and the endomorphism ring, and the map F looks like the map that sends a matrix A to minus A transpose, which is exactly what SON is. So the ring of invariants for N is the same as the ring of invariants for SL2, which is the same as the algebra SON. And so when we think of the associated graded, the degree 2 part, it should look like SON tensor our group algebra. So if there was going to be some Lie algebra G, so that H upper G is the same as Hn, then it would have to be SON for this to be true. But we know that can't be possible because this is a proper inclusion. So yeah, in conclusion, only these two reductive subgroups have this property. They match up nicely with Lie algebras. Yeah. And if you are interested, and go and read the paper after this talk, we don't really use this degree 0 notation that I've introduced so far. It just seemed a lot more natural than beginning with GLN and talking about Lie algebras. But we use the GLN notation from the start for the degree 0 subalgebra because of this link. Okay, so now we can talk about the actual results about the centers of these invariant subalgebras. So this is just a little setup slide, establish some rules here. So gamma, our reductive subgroup here, is a group of automorphisms of H. It's reductive. One, it acts trivially on the group and linearly on H plus its dual, and it preserves the symplectic form. This conjugation thing, don't worry about it too much. What it means is if we think of W acting on our space H, then okay, we just act on it. That comes with that action. But when you think of it on the entirety of the rational Cherednik algebra and you write it as matrices, it's possible to write this in a way that looks like conjugation by these. But so don't worry about it too much. Okay, and the action of the center of the group is trivial on W and it's linear on H plus its dual. And so we can also think of the image of Z of W lying inside this reductive group. Okay, so since gamma acts trivially on W, then it doesn't matter which way around we think of the invariants of these. So that's why we just write gamma cross W sometimes, and that just means that this is something the invariants under W, and also that they're invariant under gamma. So as is often the case in maths, right, you start with a simpler case and you try and generalize up from there. So the simpler case for us was to start with setting T and C both equal to 0 and seeing if we could find the center of this invariant subalgebra. And it turns out, yes, you can quite explicitly. So our theorem says if the kernel of W into GL of this space is equal to the center of the group, then we have the following equalities. That the center of the invariant subalgebra is the same as the invariance of the center tensored with the group algebra at the center of the group, which is the same as this polynomial ring tensored our group algebra. So this W into GL of here, just to explain that a bit, all that means is W has an action on H, it has an induced action on H dual, so I can think of W acting on H tensor H dual, that's all. Yeah, and yeah, so if the only thing that is in the kernel there, e.g., if the only group elements that fix everything that look like pairs of X and Y's is the center of the group, the Moss-aligned center group, then we have these equalities. So this condition might look a bit awkward, but it's fine. It's not too restrictive. It holds for any complex reflection group as long as our reductive subgroup is CX. And in SL2, there is a slight detail that the dimension of H equals 2 is a totally different case and has to be treated entirely separate, which I'll talk about briefly at the end, but very briefly because it's quite involved. But if the dimension of H is bigger than 2, then there's no problem. Then this also holds for any complex reflection when gamma is SL2. Okay, so how to see that? So first of all, looking back at this equality, we show that, I guess I should just say how to see the second equality into the third equality. So CZ of W is the same. We know what the center of the group is for this one. This was near the PBW stuff. This is just H00. So this is the polynomial ring of invariants under W. So that's why that follows. So really, we just want to show that this left-hand bit of the equality sign is equal to either of these. And so we're going to show that it's the same as the far right equal sign there. Okay, yeah, so we're going to show inclusion of the center of the invariant subalgebra first. So we take some element inside the center of the invariant subalgebra, and then we just calculate some commutators, right? So it's in the center, so it should commute with everything, so the commutator should always be 0. So we start with something inside this tensor of H and its dual under the invariance, and just work out the commutator there. Now, since T and C are both equal to 0, when you check the Cherednik relations, that means that your X's and Y's, they all commute, right? You just, it becomes the same as the symmetric algebra V semi-direct product with the group. So this U, in other words, will commute freely with the F's. The F's stand for our X's and Y terms here. So we really only have to worry about the action of the W's in this sum, which is why we get this W inverse of U appearing. So for this to be 0, we need W inverse of U minus U to be 0 whenever F of W isn't 0. So in other words, we need W inverse of U is equal to U for all W, right? And since this has to hold for every U, because A is in the center, so it has to hold for every U, this is precisely the statement, that W is in the kernel of this map, right? And the kernel of this is the center of the group, so W has to be in the center of the group. So we can rewrite our element A here not as a sum over all, just any group elements W, but just as group elements inside the center of the group. So the next thing to do is we've done the XY terms being plugged into the commutator, so now plug in some group terms. So we let U be inside the group now. So when we calculate the commutator in that case, which isn't written out here, but U is now going to commute with all the W in that sum because they're all inside the center of the group. So we only have to worry about commuting with the F. And if you write it out, it's pretty easy to see that you're going to need each FW to commute with the U's. So that means that each FW has to be invariant under these U's. And that again has to hold for every U inside W. So that means FW has to be in the invariance under the action of the group. And since AFW at the start had to be inside the invariance under the reductive subgroup, it's inside the ring of invariance under both, in conclusion. To check the other direction, take something in here and show that it's in the center of H gamma. We've essentially already done that. You just have to check what we have already checked in these relations, that it all commutes. So that direction is easy. So yeah, so to summarize, we now know how to write down what the center of the invariant subalgebra is when T and C are both 0. So now the goal is to generalize to the case when T is still 0, but C is not. So we get something that holds for every C. Okay, and so to do that, the key is to use the associated graded. Like I said at the start of the talk, it comes up very frequently. So we've got these two theorems that really tell us what the associated gradients look like of the things that we're interested in. So the first one tells us what the associated gradient is of the center of the algebra of invariants. And the next one tells us what the invariants of the center of that subalgebra look like. The second one is much easier to prove. So I'm just going to admit that now, but if you're curious, you can check out our paper. It's really not that bad. The first statement is the one that requires a bit more work and is actually much more important, really. It was kind of figuring out this one that made a lot of things click into place, and maybe the proof will illuminate some. So this is just a sketch of the proof because certain key justifications are sort of omitted. So you first need to prove this top line of equalities, which we do elsewhere in various steps in the paper. So we've got the center of the associated gradient of this algebra invariance is equal to the center of this polynomial ring, which is equal to this one. Right, and so if we compare back here, this second term in this equality is right here. So to prove it, So the second part of the very first lemma of the talk says that the associated gradient of Z of H gamma is always contained inside the center of the associated gradient. That's true just if you replace H gamma with any algebra A that's got a filtration, that the associated gradient of the center is always inside the center of the associated gradient. So we now know that this one here is inside each one of these algebras above in the equality. So we want to prove the reverse inclusion, right? And then that will give us equality with this second part here, which is the theorem. So we pick this one on the right-hand side here and show that the reverse equality holds. Okay, so by our third assumption in the setup slide, the image of the center of the group is inside our reductive subgroup, or we consider it as actions. So it's going to act trivially on elements that are invariant under the group gamma, right? If it's in gamma, it's going to be invariant on things that are invariant under gamma. So the center of the group then is inside the center of the invariance of H under gamma, just as a whole thing. And this says more specifically, it's inside the zeroth component when we give it our PBW filtration. So that means the center of the group is also inside the associated graded. So how do you see that? Well, it's in the 0th component here. The f minus 1th component is just the element 0. So in the associated graded, we've got this quotient by 0. That's going to change in nothing. So the center of the group is inside the associated graded. And then it's also always true that z of h gamma is contained inside, sorry, the invariance of the center is always contained inside the center of the invariance. That's just an identical argument to when I was first talking about comparing the subalgebras there. You had the degree 0 part at the center and the center degree 0 part. It's quite easy to see one is always included in the other. This is just the same argument, but instead of the degree 0 stuff, just do it for the invariance under this reductive subgroup. So the first part of our key lemma right at the start then says that we have this inclusion of, since this is a subalgebra, we've got inclusion as associated graded, and then you just use the second theorem here, which tells you what that associated graded looks like, and it turns out it looks exactly like this polynomial ring of invariance, which is what we wanted. So we know the center of the group, and we know this are contained in it, and we know that this is contained inside each one of these, so they must be equal. Okay, and so this now is kind of the, well, one of my favorite theorems from the paper. So this tells us what the center of the algebra invariance looks like for any C, and any reductive subgroup. Yeah, quite neatly. So it turns out it looks exactly like the invariance of the center of the rational Cherednik algebra, but with all of the center of the group terms appearing as well, with the group algebra of the center of the group. And it decomposes into a direct sum, pardon me, of the invariance of the center times by these AIs, and these AIs are just some idempotent basis of the group. It depends on your group what that would be. Okay, so the first part of this proof is just justifying that if we can prove this second line here, that we've got this direct sum, that'll imply the first line, so which is clear enough. So you have to justify that each one is free of rank 1. So when you take C equals 0, our space z of h gamma, we know what z of h naught is. That's given in the slide about the center of the rational Cherednik algebra, what we initially know about it. So we know the center is the polynomials that are invariant under W. So including under gamma, we just get this. So this is free of rank 1 over the same polynomial ring. We also have a similar result when we consider the associated graded of this algebra, z of h, the invariance of the center, times these AI. So then this is then free of rank 1 over the invariance of the center for any C, not just C equals 0. There's a little bit of a subtlety here, but it kind of follows from making an exact sequence of the components of the associated graded. And you have to use a property of reductive stuff here. But yeah, it boils down to needing to know this fact, which implies that this is then free of rank 1. Yeah, over the invariance of the center for any C. Okay, so each one of these, z of the invariance of z, we know the invariance of z are inside the center of h gamma, right? For any gamma, we just discussed that. The AI are also an idempotent basis of the center of the group, and we know that the center of the group is also contained in here. So each one of these components, this the invariance of center times AI, each one of these has to belong in the center of the invariance. So we know we have an inclusion when we just sum them all up. So how do we see that this is actually an equality? So again, we just argue on the level of associated gradeds. So since we have this inclusion, we've also got an inclusion of their associated gradeds, and then we show that they're equal. So we start with this polynomial ring. We rewrite it in terms of a direct sum of the polynomial ring of invariance in the AI. this is the same as the associated graded of this. When you see GR of HC, just think you can replace that by H0. Yep. And then the next line, we just start with the same thing. So we've got GR of this. Well, this has to be inside the associated graded of the center of the invariants, right? That's just applying GR to both sides of this inclusion here. And we know from our last key theorem here exactly what GR of ZH is. Yes. Well, okay, technically it's hidden in the proof. Right, I should have thought of. So it's this polynomial ring here times by the group algebra of the center of the group, which is exactly what we want to end up with. So both sides of these are equal. So this inclusion must actually be an equality, and we get the proof of the theorem. Okay. So that, just to sum up that stuff, so that was all the case t equals 0. We just started from the case when c equals 0 as well, talked about the associated graded, showed what they are, and then you can generalize to NEC. For t, the process is pretty different and fairly unique. So instead, what comes out is the Euler element. So if you've got some basis y1 to yn inside h, and you've got your dual basis of it x1 to xn, then the Euler element is just defined to be this sum here minus another sum of reflection type things. So it doesn't depend on any basis. It satisfies these commutation relations. And it turns out when t is not equal to 0, then the center of our invariants, just for Cx, not SL2, is equal to functions on this Euler element, tensor the center, the group algebra of the center of the group. So we get this CZ of W appearing very commonly when we look expressions of these subalgebras, the centers of these subalgebras. And I guess one of the interesting things here to note is that the center for one wasn't trivial like it is of the whole thing. Yeah, we do indeed have at least one element contained in it that's nothing to do with the. And I said I would also talk a little bit about the case where the dimension of H is 2 for SON. So when the dimension of H is 2, I kind of briefly mentioned and ignored this conjugation action by the group. So when you write it down and you start acting on things explicitly by conjugation on this space H tensor its dual, in higher dimensions, you can conclude that a lot of your matrices that you want to write out explicitly have a lot of zeros. They're forced to have many zeros. And so things look like scalar actions a lot of the time, which is part of the kind of underlying machinery for why a lot of these results come out so neatly with just centers of the group being our group algebra that we're tensoring with. But in the case where the dimension is 2 and you've got SL2, there's not enough space to force a lot of these things to be 0. You end up with I think it's in our paper, and I think it's you end up with some kind of scalar multiple of the identity, but also plus some skew symmetric matrix, which makes it quite difficult to understand the center. So you have to treat that case entirely differently. And it's got a pretty big proof, so I'm not going to cover it here. But what you get is this, which is pretty interesting, why its behavior is so odd. But in this case, the center just looks like a lot of polynomial rings stuck together. So these M12s are they're the same element that we defined for the Dunkl angular momentum algebra. So this is just x1 y2 minus x2 y1, and these b's and d's are group things. Yeah. So yeah, you end up with something much more complicated, funnily enough, for the low dimension case, but higher dimensions are fine. Okay, so in summary, yeah, the degree 0 subalgebra and the Dunkl angular momentum algebra are interesting objects, and maybe not always, but certainly for our case, for our purposes, it was much easier and more natural to think of them as being subalgebras, as being invariant subalgebras under the action of a reductive subgroup of SL2. To make the most success in understanding their centers, we tried to compare them with the center of the whole rational Cherednik algebra and look at its invariants. And to do that, what you needed was the associated graded and just some simple properties that follow from the associated graded can get you really far. And then, as you'd expect, when you change the parameter t, it'll greatly change the center of these subalgebras. But the center of this, the group algebra of the center of the group still seems to appear quite often. So, yeah, and all of these results with much more details can be found in our paper that's on archive right now. It's called Two Invariant Subalgebras of the Rational Cherednik Algebra. Yeah, and we cover quite a lot more stuff. That's just one flavor of the paper. But yeah, so anyway, thank you for listening. And if you have any questions.
Okay, thank you very much. Are there some questions? You simply can speak without asking for permission.
Yeah.
I cannot see any questions. Thank you once again.
Yeah.
You're welcome to listen the other talks when we announce them. So you're already in the list.
Right. Okay. Yeah, sure. Sounds good. Okay. Right. Well, I guess I'll stop sharing my screen now.